Hi, everyone. This talk is again about simulating a certain class of quantum circuits. In this case, it's going to be quantum circuits which are low depth and geometrically local, and I'll say a little bit more about that in the next couple of slides. It will be a little bit different from the previous talk, perhaps in the sense that the previous talk was about a simulation algorithm and how well it performs in practice. And here we're going to be talking about the scaling of this algorithm asymptotically. So what is the provable scaling of this algorithm asymptotically? Yeah, so that's one difference. All right, and this is, I'm Matt Coudron, and this is joint work with Nolan Coble. Okay. Oh, my slide transitions. There we go. Okay. All right, so let me define now, or give a little bit more detail about the problem statement. So here's the computational problem we want to solve. You are given a geometrically local quantum circuit. So here I've drawn a one-dimensional version of, or one-dimensional diagram for this. So this is a 1D local low-depth quantum circuit. So you can get a sense for what geometrically local means. It means the 2-qubit gates. Our circuits are always going to be comprised of 1 and 2 qubit gates. It means that the 2-qubit gates are only applied to nearest neighbor qubits. Okay, in this case on a line, although I'll be showing in the next couple of slides the 2-dimensional case and the 3-dimensional case. All right, and our goal is to approximate this quantity. So this is the probability that if you start with the all zero state, act on it with this geometrically local low depth circuit, which I'm going to call C, and then measure in the computational basis, this is the probability that you get the bit string X as the output. All right, so our goal is to approximate this output probability additively, so to an additive plus or minus an additive error epsilon. Okay, and as I mentioned before, we consider not only the 1D geometrically local case, but also the 2D geometrically local case. So that's shown here. Here, the depth, you notice I've drawn a 3-dimensional object. So the depth is the vertical dimension. So that's the number of layers of gates that's required, or that comprise this circuit. And the grid, the other 2 dimensions are the locality. So gates are allowed to be applied along nearest neighbors, any pair of nearest neighbors on this grid. Okay, and we're considering the complexity of estimating this output probability in the worst case over all such quantum circuits. All right, the complexity as a function of n. So this is an n-qubit quantum circuit, and we also allow arbitrary 2-qubit gates. Right, so any 2-qubit unitaries can be the gates. All right, so this is what the 2-dimensional case looks like. It takes 3 dimensions to draw it because the depth takes 1 dimension. So if I show you the 3-dimensional case, well, I've sort of punted on trying to draw the 3-dimensional case because it would take 4 dimensions if I would include the depth. So you'll just sort of have to imagine what that 3D geometrically local quantum circuit might look like. At least one layer of the circuit would be geometrically local gates applied on a cubic lattice. Okay, and again, we consider the same problem. We want to estimate output probabilities. So that's our problem statement. Let me talk really briefly just about why should we be interested in this task. When you hear about these types of circuits, geometrically local and low depth, a lot of people might immediately start thinking about sampling problems, or perhaps about some kind of adaptive measurement procedure, measurement-based quantum computation or something like that. Those types of tasks typically would be more related to the regime on our additive approximation error is exponentially small. All right. And we're going to consider a different regime. And so that's why I want to explain the motivation for that. But let me just say briefly, when epsilon is very, very small, so it's 2 to the negative n squared, where n is the number of qubits, we actually know that this task of estimating this output probability is sharp p hard. All right, so that's one reason to be interested. If you make epsilon small enough, you're somehow, you're kind of scaling between, well, you're scaling up to a very computationally complex problem that you may be interested in. But this also means that we can only hope for an efficient solution to this problem when epsilon is much larger than this 2 to the negative n squared. All right, we're going to actually focus on the case when epsilon is inverse polynomial. And so why would we be interested in that case? Okay, so that's perhaps more related to a case where you are applying your quantum circuit, measuring the output all at once, and then feeding the classical bit string that's the output into some classical post-processing to compute some quantity. So this is sometimes done in hybrid quantum algorithms. And so one potential application of this is classically simulating hybrid quantum algorithms. All right. So I think the setting to think about to motivate yourself for this problem is this setting, quantum circuit followed by classical post-processing. Okay, and our algorithm, our classical algorithm that I'm going to present here in this presentation it actually solves a few special cases of this, some very special cases of this, right? So we can solve the case when this classical post-processing consists entirely of an AND gate, the logical AND gate on all of the output wires, all right, all n of the output wires. We can also solve the problem when it is the logical OR gate. We can handle any negations of those wires with that single gate. And also, interestingly, and I won't get into the details here, but we can also solve this problem when it's an XOR gate. So when it's the parity of all the output bits, right? This line down at the bottom of the slide, if you can see it, just states why we can actually, all of these problems can be solved, and actually the original problem can be solved. We can, without loss of generality, reduce to just estimating the output probability of the all zeros string. Because the output probability of any other string can be computed that way by just absorbing that string into the low depth circuit. All right. So from now on, we're just going to consider estimating the probability of outputting all zeros. So some other reasons to be interested in this problem. Our algorithm can also estimate the expectation of a Pauli operator. So this product of the PIs is meant to be Pauli operators, one on each qubit, a different one on each qubit. The expectation of this state on this Pauli product operator. So that's maybe a more physics motivated application. And then a final reason to be interested at the level of techniques. In order to estimate these quantities, we are somehow controlling something about, or computing something about global correlations of all in output wires of this circuit, even though the light cones of those output wires overlap quite substantially. And I'll say later on what a light cone is. Okay, so that's some motivation. Let me give you some quick background. I mentioned before the 1D. So this is some known results. I mentioned the 1D case of this problem before. There's actually an easy solution, or a well-known solution to the 1D case of this problem, and it works using matrix product states. And that's all I'll say about that, just for time. The 2D version of this problem is not so immediate. It's non-trivial. It seemingly can't just be done with the standard application of matrix product states. However, there is an elegant algorithm due to Bravi, Gossett, and Movesog that does solve this problem. And it's too bad I don't have time to even give a brief description of it because it's very nice. And their algorithm will give an epsilon approximation of this output probability in time that is polynomial in n, the number of qubits, and polynomial in 1 over epsilon. Okay. And we'll actually end up using that as a subroutine later on in our algorithm for the 3D case. Okay. But first of all, going to the 3D case, so 1D case and 2D case are solved. The 3D case is interesting in a sense primarily because the Bravyi-Gossett-Movisog techniques don't seem to extend there, at least not in polynomial time, right? So it's unclear how to use those techniques to get a polynomial time algorithm for this case, or even one that doesn't scale exponentially. So BGM, I'll abbreviate Bravyi-Gossett-Movisog to BGM. So BGM they show how to use their techniques to produce a sub-exponential time algorithm. So an algorithm for the 3D case, an algorithm that runs in time 2 to the n to the 1/3, where n is the number of qubits. So it is exponential in the side length of this cube. But it's unclear to get further than that. Okay, so enter our main result. So the main result of our work is that we give a classical algorithm that solves the 3D case of this problem in quasi-polynomial time. So we can give an additive error approximation to any inverse polynomial error. Actually, we get inverse quasi-polynomial error, which beats any inverse polynomial error. And we can do real time. And at this point, if you didn't know what quasi-polynomial means, it means n to the polylog n. Or you can think of it as just being n to the log n if you want. So that's what quasi-polynomial time means. And our algorithm also depends on the depth in a specific way. It's exponential in the depth d. Little d is the depth of this circuit. So it will be quasi-polynomial time for constant depth circuits, but also for logarithmic or depth circuits. Okay. So just to reiterate, this algorithm worst case over all circuits. It works provably, and it works. Our gate set is arbitrary 2-qubit unitary gates. We actually believe that this algorithm will generalize to any fixed constant dimension greater than 3, but we only prove in our paper the 3D case. Okay. So since I'm a little bit short on time, let me I'm just going to jump immediately into talking about techniques and lemmas and ideas that go into this algorithm, and then later on I'll define the actual algorithm for you. So since we're unable to directly extend the techniques in the BGM paper to this 3D case, at least we can't do it any better than they did. We basically go back to the drawing board. So our intuition just goes back to the types of properties that people would always think about for simulating geometrically local low depth circuits. And that is that the light cones, and now I'll finally tell you what a light cone is if you don't know, the light cones of output wires in these circuits are local. So what do I mean by a light cone? Well, imagine you have this cubic circuit, and imagine cutting it in half with this purple slice. So it has a left half and a right half, and this purple slice of qubits, right? So qubits are laid out on this cube. This slice contains a kind of 2D array of qubits. And if you take such a slice, then you can imagine all of the gates that are directly or indirectly connected to the qubits in that slice. And you can see over on this bottom right-hand side what that might look like. It's all the purple gates here, right? So those are the gates in the light cone of the register of qubits called M. We're calling this slice M. Okay, so that's what I mean by a light cone. And you can also think of all the qubits in the light cone, which is all the qubits down at the base of that purple cone. Okay. So the intuition is that somehow the left and right-hand sides of this slice, if you make the slice a constant width, those are light cones separated from each other. They don't touch each other somehow, and you can, in a sense, compute many properties of them independently from each other. So you could hope that perhaps you can express the output probability over the whole circuit as some simple expression that depends, only on the, some, chopped up pieces of the circuit. And this would lead to what we would call in classical algorithms a divide and conquer algorithm. Sorry, I shouldn't have. Yeah, so our goal is the divide and conquer algorithm. And so now I will, we will find such a recursive algorithm, and I'll start to explain now, and things will get a little bit more technical now, how that algorithm works. So here's a more technical motivation for this divide and conquer algorithm. Imagine a state, psi B union F. Okay, so this is a quantum state on the registers B and F illustrated here. And the way that we construct it is, so by the way, I'm drawing the gates here in 1D form, but this is actually meant to represent a slice through a 3D circuit. I'm just drawing it in 1D because it's easier to draw. Okay, so imagine a quantum state which is produced by applying, starting with the all zero state on B, M, and F, and then applying only the gates that are purple, only the gates in the light cone of M. That's this circuit CBMF, okay? And then projecting onto the all zeros state just in the M register, which leaves the B and F registers unmeasured. So psi is an unnormalized quantum state on B and F. So this state represents, in a sense, how much entanglement or information is going across this slice M of our quantum circuit. Okay, and so naturally we would look at its Schmidt decomposition. So that's here on the far right. If it turns out that the Schmidt decomposition of this circuit has most of its mass in the high Schmidt coefficients, then in this equation here, we can see that we can actually write the original quantity we care about, the output probability of all zeros, as the sum of some new quantities, each of which are products of output probabilities of geometrically local low depth circuits of about half the size. These are CL and CR. So those are the blue gates and the red gates, respectively, and they correspond to the blue and red parts of this cube up here. Okay, and so that's exactly how we would want a divide and conquer algorithm to work. It expresses the original quantity as a simple sum or a simple expression of new quantities that are the same type of problem instance of only about half the size. Okay. However, there are two problems with this approach. One, we assumed that this state, psi BF, has most of its mass on just a few Schmidt coefficients, but why should that be true, or how could we prove it? And then the second problem is this divide and conquer approach that I've outlined only works, you're only expressing the original problem as new problems of the same type if you can construct the Schmidt vectors, V and W of psi. If you can construct those vectors themselves with a low depth geometrically local quantum circuit. And in this case, we would want a 2D circuit because we're taking a 2D slice. It's not clear how to do this, and a priori, it was not clear that you even can do this. Okay, so we're gonna solve these two problems. I'll explain how. We're gonna start with problem number 2. All right, how to construct the Schmidt vectors via a low depth geometrically local quantum circuit. So long story short, I wish I could do more build up to this, but I don't have time for it. We're going to use a technique called block encodings to do this. And block encodings are a standard technique from the literature. I will explain them in the next couple of slides. But first, if for people who are familiar with them, I just wanted to point out that traditionally block encodings are used in quantum algorithms. But here we are using them as a subroutine of a classical simulation algorithm. So we are actually using them to construct circuits which we use to implement a division step in a divide and conquer classical simulation algorithm. So I just wanted to mention that because I think it's cool. All right, so here's what a block encoding does. Let rho F be the density matrix corresponding to the F register of psi BF. A block encoding allows you to construct rho F using a low depth geometrically local quantum circuit. In this case, it's just a simple composition of CBMF and a swap gate in a particular way. And then you have to project onto 0 in all of the registers that are not the F register. Okay, so that's what it does. And it will also let you produce the kth power for some integer k of rho of F. And that's in a not too much more complicated way. I won't go into detail here. So the key idea that we're using here is that if the Schmidt coefficients of psi are gapped, the first and second Schmidt coefficients of psi are far enough apart, then this kth power of rho sub F actually approaches something proportional to a projector onto the first Schmidt vector. And that's what we're going to use to sort of construct the Schmidt vectors with low depth geometrically local quantum circuits. Okay, but of course there's a problem, which is how do we know that the Schmidt coefficients are gapped in this manner, right? And this is related to the original problem number 1. How do we know that most of the Schmidt mass, or most of the mass of the Schmidt coefficients is on just a few Schmidt coefficients? So it turns out that the way we solve that is it turns out that if you assume that the quantity we want to compute, this output probability of all zeros of this cubic quantum circuit, 3D local quantum circuit, is at least quasi-polynomially large, then it is true that you can find, or there exist, and you can find many slices across which the first Schmidt coefficient is very large. It has about 3/4 of the mass. Okay, and we can take this assumption that the output probability is large because we can actually check all the slices in polynomial time and determine if this lemma holds. If the lemma doesn't hold, then we know that the output probability is smaller than quasi-polynomially small, in which case we can output 0, and that's a valid additive error approximation in our case. Okay. Oh yes. So the reason we can check this is we can actually compute the Schmidt coefficients of these 2D slices using the Bravi-Gossett-Movisog 2D algorithm that I mentioned before. And the procedure for that is involved, and I won't cover it. But that's how we can actually check for these heavy slices. Okay, so on these heavy slices, we know that we can actually construct the leading Schmidt vector. So this is progress. We've solved 2 of the problems that we encountered. All right, we can construct the leading Schmidt vector with the geometrically local constant depth or low depth k quantum circuit. Okay, I'm going to run just about 2 minutes over, I think. So there's another problem, which is that we've only managed to construct the very top Schmidt vector in this manner. All right, not all of the Schmidt vectors. And so what this means is that since the top Schmidt coefficient has 3/4 of the mass, we can approximate the desired quantity by, sort of a product of smaller instances of the same problem, but our error term is size 1/4. And that's terrible. That's a constant error. We want to have error that's inverse polynomially small or even inverse quasi-polynomially small so that it decays with n. So in a sense, we might still be very far from our goal here. So we have to make another big step, which I'll abbreviate quite a bit. But the intuition to solve this error problem is that instead of doing a division step about 1 cut of the cube, we actually do a division step about many cuts of the cube, delta cuts, and we perform an inclusion-exclusion process, which I won't go into in detail. Yeah, and I'll go through this relatively quickly, but the theorem statement here is that the quantity we care about the most, this density matrix of C acting on all zeros, the original circuit, can be approximated by a big sum of density matrices psi. Those density matrices psi themselves are comprised of density matrices phi, and the density matrices phi can be constructed using the Schmidt vectors across various cuts with geometrically local constant depth quantum circuits. And these circuits are about half the size of the original circuit. So that's the key, is that the original quantity can be re-expressed as the sum of using geometrically local quantum circuits acting on about half the number of qubits. And the error term is exponentially small in the number of cuts. Yeah, okay, so I have, I think, one more minute. Exponentially small in the number of cuts, so we're taking delta cuts. So now I can define the algorithm, and that's the end. So it's basically just this slide. So using this inclusion-exclusion argument, our algorithm is the following. We define it as this algorithm A. It takes as input the circuit diagram for the circuit that it cares about, and a few other parameters, including delta, the number of cuts that it makes. And its goal is to estimate the output probability of all zeros within some additive error. So the first step is we find log n light cone separated heavy cuts that are close to the center of the cube. So we can do that using the 2D algorithm of Bravyi, Gossett, Movisog. And the next step is we compute the Schmidt coefficients across those cuts, again with the same algorithm, circuit diagrams for these phis, which I showed how to construct previously. I'll show again. It's okay if you don't understand that. All that matters is their geometrically local constant depth and half the size of the original. And then you just return this quantity, which corresponds directly to this inclusion-exclusion quantity. And the key, this is very complicated. It's going to be hard to internalize, but the real takeaway from this is that these A terms here are recursive calls to the same algorithm that we just defined. We're saying we just make another recursive call of the same algorithm on a smaller, now smaller circuit diagram. And now I'm out of time, so I'll, the rest of this is just restating the main theorem that this algorithm works in quasi-polynomial time. And then I talk about runtime analysis and error analysis, but very briefly, but I'm out of time for that. And that's it. So I'll go to questions. Thanks for sticking with me.
Thank you very much. Okay, so we have 3 questions, and we'll see if we can get to all of them. So see how. So one question is, if you apply your sorry, RT Sundaram asks, if you apply your algorithm to lower dimensional circuits, i.e. 2D or 1D, would you recover the previous results from BMG? Or was there something specific that works only for 3D circuits?
Okay, good question. I think, well, our algorithm uses the BGM algorithm as a subroutine. So in some sense, if you were going to use our algorithm on the 2D case, you might as well just use the BGM algorithm directly on the 2D case. We're not going to outperform it on those lower dimensional cases because we actually use it as a subroutine. So okay. We can't, yeah.
Okay, great. So Rolando Soma asks, can these ideas be applied to the simulation of log depth 3D non-unitary circuits?
Oh, I'm not sure if I know exactly what a non-unitary circuit is. However, I will say, that we do allow you to project output registers onto like particular measurement outcomes. So like some kind of conditional unitary, what we call a synthesis in our paper, but may be called other things elsewhere. Yeah. Okay, great. So I think we are out of time now, so we'll leave it at that. So there is another question, but we'll move that to the we'll ask that to be taken up in the round table.
And I believe in your viewer, if you click on the bottom left, you're taken to the roundtable, and there is a separate roundtable for each of the 3 talks in this session. So thank you very much, Matt, and thank you very much all 3 speakers. And this is the end of the session.